Okay, we're just completed part 4 of chapter 13. We're going to continue on. I'm going to dismiss my image. And what makes an object float or sink? Whether an object floats or sinks depends upon the volume of the object, the volume of the fluid displaced, those two items, the volume of the object and the volume of the fluid displaced. So an object floats on the surface of a liquid if the weight of the object equals the buoyant force exerted by the fluid. The object's weight equals the weight of the displaced fluid. Okay, let's see. 3 rules. An object more dense than the fluid in which it is immersed will sink. An object less dense than the fluid in which it is immersed will float. An object having a density equal to the density of the fluid in which it is immersed will neither sink nor float. It will remain submerged at a constant depth. I had mentioned previously that Southwest Research had a little program where they mapped the inside of a cave that was filled with water using a little device. It's like a little ball that had neutral buoyancy, so that it would neither rise nor fall, and it was able to map out the inside of a cave. Now it's 2 solid blocks of identical size are submerged in water. One block is lead, the other is aluminum. Upon which is the buoyant force greater? Now, on the lead block, on the aluminum block, it's the same on both blocks. There's not enough information to decide. Well, the buoyant force is equal to the amount of water displaced. If they're identical size, then they displace the same amount of water, so that's the same on both blocks. Now, whether one sinks and whether one floats, or how much it'll sink, the lead would obviously sink greater because it's greater than the volume of the water displaced. The buoyant force depends on the volume of the block that is submerged. Since both submerged blocks are the same size, they displace the same volume of water, so they have the same buoyant force. Okay, now we're going to go on to Pascal's principle. Pascal's principle says that it was discovered by Blaise Pascal, the scientist and theologian in the 17th century. It states that a change in pressure at any point in an enclosed fluid at rest is transmitted undiminished to all points in the fluid. And it applies to all fluids, gases, and liquids. So if you push a little bit here, that pressure is going to be felt all over. Now, the application in hydraulic press. So the pressure is applied to the left piston and is transmitted to the right piston. So a 10-kilogram load on a small piston lifts a load of 500 kilograms in the large piston because it's the area here. This one says 50. The area is 50 times as large as area A. So the 10 kilogram is the same as the 500 kilograms on this larger area. Okay. The application for gases and liquids is seen in everyday hydraulic devices used in construction, in auto lifts and service stations. Increased air pressure produced by an air compressor is transmitted through the air to the surface of the oil in an underground reservoir. The oil transmits the pressure to the piston, which lifts the object. It's just a hydraulic lift, basically. And it's a conservation of energy principle at work here. In a hydraulic device, it is impossible for the output piston to move further than the input piston. No, that it's possible to do that. The force output to exceed the force input. Well, no, it's possible to do that. We saw that with the 10 kilogram and the 500 kilograms. The output piston speed to exceed the input piston speed. Well, it could do that. the energy output to exceed the energy input. Whoa, there we're violating the conservation of energy. And that one cannot, remember it says in a hydraulic device, it is impossible for the energy output to exceed the energy input. And there's the answer. Okay, surface tension. The contractive tendency of the surface of liquids is due to surface tension. So if we were to have like a slightly, a very delicate wire, and we have this bent wire, when you submerge a wire in water and pull it out with a spring, the string stretches because the water is actually pulling it back because of the surface tension. When you place a paintbrush in water and pull it out, the water contracts and pulls the hairs together, all because of the surface tension. Other examples of surface tension. Drops of any kind are spherical because the surfaces tend to contract and force each drop into the shape having the least surface area for a given volume, a sphere. I know raindrops are typically painted or depicted as teardrops, but they're actually spherical. Now, they might be bent out of shape because of air pressure, but their natural state is to be spheres. That's the least, the surface tension will cause it to be in spheres. Bubbles are spherical for the same reason, surface tension. Okay. Surface tension is caused by molecular attractions. Beneath the surface, each molecule is attracted in every direction by neighboring molecules. A molecule on the surface of a liquid is pulled only by neighbors on each side and downward from below. There's no pull upward. These molecular attractions tend to pull the molecular, these molecular attractions tend to pull the molecule from the surface into the liquid, causing surface tension. Okay, factors affecting surface tension. The type of liquid, water has a greater surface tension than oil. What is mixed with the liquid? Soapy water has a lower surface tension than water without soap. The temperature of the liquid. The molecules in a hot liquid have a higher energy and are not bound tightly as in a cooler liquid. So all of those will affect surface tension. The rise of a liquid in a fine hollow tube or in a narrow space is called capillary. I mean, this could be a cross section of a tube, or it could be two plates of glass very close together. Adhesion between the molecules of the glass and water draws the film of water into the tube. Now, when you have two different materials, it's called adhesion. Cohesion is when the water molecules staying together. That's cohesion because they're both water molecules. But adhesion is because when you have something like glass and water. So adhesion between the molecules of the glass and water draws the film of water into the tube. The surface tension causes the film on the surface to contract. This raises the liquid from below to rise in the tube. It's going up. When the force of the surface tension balances out the weight of the liquid stops rising. So this weight, the surface tension equals this weight, it will no longer rise. Okay, now the height of rise depends upon the weight of the liquid and the narrowness of the tube. You can see with the narrower tubes, it goes higher. The lighter the liquid, the higher the capillary rise. The narrower the tube, the higher the capillary rise. Examples are oil rises in a wick. You have an oil lamp, you put this piece of cloth, the oil will rise on the wick of the lamp. The hair let loose in the bathtub causes the scalp to get wet. You don't have to put your whole head in it. You just put that's assuming you have long hair, the water will be drawn up into the hair and eventually reach the scalp. Insects have a hard time getting out of water when their legs get wet. There are some water striders, some bugs that are able to handle basically walk on water. And that's the end of capillary action. And that's the end of the chapter. We'll end it here.